Appreciate being here and sharing this topic with you. It's a great passion of mine. And regretfully, a lot of the research projects I'm involved with using BayesiaLab, machine learning, causal learning are either classified or expert controlled nature. And so I'm not allowed to talk about those in public. But there is one project that is, I can talk freely in the public, and that's what I'll talk to you about. It's called SCOPE. I am at the Software Engineering Institute, Carnegie Mellon University. We're a federally funded research and development center. And even my daughter in Iowa isn't quite sure what I'm doing. And she tells all of her extended family out there that I work for the CIA because I travel a lot. But I'm mostly doing research and consulting different DoD entities on the use of causal learning, machine learning, and applied statistics, and Six Sigma topics as well. So today's topic is not a presentation of detailed research results as much as a discussion of the research methodologies that we're experiencing, and we're on a journey related to machine learning and causal learning. And my intention on the talk was to expose you to these methodologies and at the end pose a number of questions we'd like to get more answers on, and maybe hopefully engage folks in the audience to work with us over the next several years and see if we can get more definition on those questions and the answers. So I'm going to talk a little bit about our one project I can talk about called SCOPE, talk a little bit about our use of BayesiaLab, and then talk causal learning, comparison of some of the graphical results that we get from machine learning versus causal learning and how they can be different, and then the questions that we'd like to get answers over the next several years. So our research project called SCOPE, it's a 3-year research project funded by the Department of Defense. And basically the DoD had a challenge probably about 5 years ago to have Defense Department projects with significant software components doing a better job of cost estimation of that software project activity really early in the acquisition life cycle. And to do that, we sat down and looked at the existing cost estimation machinery out there, and the inputs to that presume so much detailed knowledge that wouldn't be available until later in the acquisition life cycle that we decided we had to think out of the box and do something completely new. So we basically looked around and we saw what Shell Oil was doing with scenario planning workshops, and we ended up defining a method called QELS, which is quantifying uncertainty for early life cycle cost estimation. And we married up the scenario planning workshop with long-term thinking, with dependency structure matrices, and that all led to a Bayesian belief network model that was subjectively derived from our workshop. And then we would exercise scenarios in that model and drive, and the outputs in that BBN model would then help to inform inputs to a lot of the existing cost estimation machinery. So that was the prediction type activity prior to 2017. And then in 2017, myself and another researcher, Mike Conrad, we became much more enamored with causal learning being added to our toolkit. And we lucked upon finding out that we had some world-renowned experts in causal search that were over in the Department of Philosophy in the Dietrich School of Humanities. And I would have thought they'd be in the Department of Statistics or Computer Science. And so it was a matter of luck that we ran into them. And then through them, I learned all about Judea Pearl, and then woke up to a lot of other big names in this field. So now in our research going forward for the next several years, we're talking to the DoD about, we want to get beyond cost estimation and look at prescriptive modeling that would actually advise the DoD on the factors that you could negotiate or that projects could control to then change outcomes to the better. And so you can see here that there's a number of areas of topics, independent factors, that we believe should be looked at again, revisited, for their causal link to outcomes of effort and cost. And I can let you know it's been a wake-up call because so far in the studies that we've done, they're preliminary, but as we've revisited a number of data sets and a number of historical publications, we have found that anywhere from 30% to 80% of the factors that were deemed statistically significant in a correlation or machine learning study were not causal on effort and cost. That was a huge wake-up call. So that made us realize, wow, we really need to pay attention to the adage that correlation is not automatically causation. So from our standpoint of BayesiaLab, our use started out pretty small scale because we only had like 10 to 20% effort dedicated to applying machine learning. It's grown now to where there's like 3 to 4 of us full-time applying machine learning, causal learning. So we're reinforcing our skills and learning at a greater pace. But we are looking at supervised machine learning on schedule, quality, and cost. We're making great use of an outlier analysis that Lionel added to the tool. It's been a big time saver. I'm not sure if others have used that or tried it out, but we are researching a number of situations where knowing where the outlier behavior is important to us. And that can be in many different research projects, including the cost, schedule, and quality, but even in projects related to national security and other things like that. We also appreciate the data imputation ability, the prediction of what-if scenarios. We are now heavy into classifier development and woke up to the fact that we do need to be sensitive to whether or not we have balanced data or not when we're in certain situations. That does help in improving the confusion matrix. We also like to use these models of BBNs to do diagnostics. A number of our projects that we coach at the Air Force bases are actively using BBNs to help diagnose what's the set of events that led to what we're seeing today. And that really helps their management make certain decisions. We also are getting into affordability analysis as well. Okay, so let me talk about causal learning. And so the question is, why do we care about causation? And already explained that, it's really a misnomer to think because you have a correlation or a statistically significant result that it represents a causal link. And I'm somewhat aggravated every morning. My wife listens to NPR in the morning, and I don't know how many people listen to NPR in the morning, but National Public Radio, but they do feature like some latest research result, and it just drives me crazy that they always stop with a correlation result. There's no mention about going into causality. And so I guess the word just needs to get out about this kind of stuff. But this is one graph of a number that you can see on this one site where, it's making the point almost in a silly way that many things can be correlated. It doesn't mean anything about causation. And one other point to talk about in real terms about being fooled by correlation, we could look at the correlation between ice cream sales and shark attacks and make an uninformed conclusion that there's some causal link there, when in fact, what's often happening in the research is that there's an unmeasured confounder on both of those factors that is causing you to see that correlation. And so this is one of the reasons why a lot of correlations turn out to not have causal basis and are actually distractors to us. So anyway, that's one of the ways that we can be fooled by correlation. So it's not just correlation though that can be, can fool you in terms of thinking about causal links. So regression is built on the machinery of correlation. And so regression and methodology that is formed on association can be at risk from a causal thinking standpoint. And so you have to be careful about what's causal association and what's spurious association. And so it's really awakened me to the fact that from now on, whenever I'm doing a model, especially a regression model, I will always have the directed acyclic graph that represents my frame of reference or my theory on paper in front of me. Because the same regression model could have many different graphs in front of you, and that model will only make sense for one of those graphs, and for the other graphs it's inappropriate. And it might even be that you've included factors in your regression model that you should not have. And so it gets down to having this the structural graph and being able to block the non-causal paths so that you can determine the actual causal influence of one factor on an outcome. And then, so the point is you want to have that structural causal model in mind, whether you have searched and found it or whether it represents your hypotheses. And it's just a good communication mechanism. And BayesiaLab is great at offering us that graphical representation. So after about the past 2.5 years of myself and my coworker, Mike Conrad, looking into causal learning and looking through the literature, we came to several conclusions. One is that a lot of the researchers that are making great advances in this methodology and using it are interested in getting their own research done with this tool set. They're not in the transition mode of telling other people about this great thing. So when I first went over and talked to them, I said, you're the world's best kept secret. We got to do something about this. So anyway, it was a little tough, but after about a year of talking to them, looking at the literature, my view of the causal learning landscape is on this slide. And so basically, in a nutshell, there's a lot of body of knowledge that talks about going from raw data to a directed acyclic graph. And that's called causal search or causal discovery. Then there's a completely other set of body of knowledge that goes from that graph, that causal structure, to actually estimating the quantified causal influences on the links, whether it's direct effects or indirect effects. And what we found was that there are different people in the world and in this country that are working on each of those parts of the landscape. So the faculty at Carnegie Mellon University, they're really strong and they're well published in causal search. And you're going to see that they have a myriad of algorithms that actually can look at data and actually tell you what the evidence shows for causal links versus spurious links. And then on the other side of the world, there's Dr. Pearl and many others that have really matured the body of knowledge of taking directed acyclic graphs and making many conclusions from those. So I just want to let you know that the CMU folks have created an open source tool called Tetrad, and it's been out for about 10 to 15 years, 12 years. And anyway, it basically lets you do basic causal search. It does have some estimation support for very simple models, and I'm not going to go into that part today. But anyway, I put some links on here if you want to look more into this, but I would let you know that we are using both machine learning with BayesiaLab and causal learning with Tetrad hand in hand. And some of the questions I have at the end of this presentation is, I'd like to look at more of the synergistic opportunities of using those two together. So this is like the bringing in the data set window. And then a key aspect in Tetrad is you have the opportunity to do what's called a knowledge box. And that is if you have prior knowledge of relationships that either must exist, causal relationships that must exist, or that would not exist because of violating temporal order, this knowledge box is where you can put that information in. So in a nutshell, the way to read this slide is you see the tiers here. Causality must flow from tier 1 downward. And so tier 1 is normally where we would put factors that we definitely treat as exogenous. Okay, they're not going to be potentially causally influenced by anything else in your data set. Okay, and tier 3 is where you might put factors that are strictly endogenous and won't really be causing other factors in your data set. And you can have varying number of tiers here. So you can get pretty sophisticated, or you can have 2 tiers, or you can not even use this knowledge box. Okay, so that is an ability there to implement prior knowledge about causal knowledge. There's a host of search algorithms in Tetrad. I'm thinking there might be as many as like 25 right now. CMU is developing and publishing about 2 new algorithms a year. It's the subject of much of their PhD student focus. But I would say that the algorithms tend to grow in 2 camps, constraint-based and score-based. There is some hybrid. And I wanted to also let you know that the output graphs from Tetrad will give you one of these 4 scenarios between 2 nodes. You'll either have no edge at all, which means that the data does not support any causal conclusion related to those 2 nodes, or you might have evidence that there is causation from A to B or from B to A. And then additionally, there are a small set of search algorithms that literally have the ability to give you a double-headed arrow, which means that there is an unmeasured factor that you do not have in your data set that is in a confounding position between A and B. And we have found that useful already because it lets us know where to shine the spotlight in the cave to learn more. And so we're using that quite a bit. Just to let you know that this is not magic, one subset of the algorithms actually operate in determining causal direction by looking at residuals and comparing them. So if I had 2 factors and I do regression with one X and one Y, then have them switch places and do the regression again, literally you can look at the set of residuals and confidently draw conclusions about the direction of causality. So it is pretty eye-opening at the different techniques that are used in these search algorithms to do this. And added a couple slides here based on yesterday's conversation. These techniques, these search algorithms are pretty robust. And this is one situation where there was a data set with only 47 rows of data observations, and there were like 21,326 columns. And basically using the search algorithm with just 47 observations, they concluded that there were 9 factors that were causally linked to I think the flowering time for this plant. And in subsequent experiments, they confirmed 4 of the 9 are confirmed through experimentation. So that was like a huge, interesting aspect of the nature of the way these algorithms can work. So both in cancer research and in some of our studies with the DoD, we are now using causal search algorithms to at least reduce the search space or the space of factors that they're going to actually conduct very expensive experiments on. And so that's a big help. So anyway, one of the latest algorithms that came out is called FASC. And FASC is an algorithm that's very much suited to skewed data and to the ability to actually pick up if there is like a bidirectional causal relationship between factors. And so I just wanted to let you see an instance of the dialog window there. There's a number of input parameters that you input and can do sensitivity analysis on. There's more factors here. Just had that for reference. And so this is an example causal structure graph output. And this is a real life data set where we were revisiting a data set of some software architecture research, where they were looking at 4 different architecture pattern violations for which ones might actually be causing quality and cost and effort to go up on a project. And they were looking at 9 open source software products out there. And in their first publication with the IEEE, ICSI, they had concluded that all 4 had high correlation and looked significant statistically with the outcome. But in subsequent uses of some search algorithms, the only one that's actually showing causal link is the number of cyclic dependencies. And so that's a very useful outcome, because if that holds through additional searches and confirmation, what it means is that it would have been inappropriate for management to have exerted control on 3 of those patterns if they were trying to change an outcome on quality and cost. And so we can also, from the tool, get the Markov blanket for any factor or set of factors. And so this was the Markov blanket for the numbugs factor, our outcome. And in the tool, you can go and do traditional SEM here, or you can get out and use other tools to come up with that output. And then I wanted to highlight that some of our key references here include a primer that came out that Dr. Pearl authored, I think 2 or 3 years ago, and then his most recent book of Why. In the book of Why, it doesn't have as much treatment on causal search as I was hoping, but it does refer to the CMU folks and their work in that area. And then we're also looking at other techniques called propensity scoring and instrumental variables to conclude causal effects. So this is all in our toolkit. So just, some of the questions that we had, we are seeing some differences when we look at like a Markov blanket from our causal learning machinery and then one from the BayesiaLab machine learning machinery. And so, the question is, how do we react to that? Okay? So, on the machine learning side, at least the one algorithm we ran, it looks like 3 of the architecture patterns are in that Markov blanket. So here's the kind of questions that we have that we would like to engage with others as we continue this journey. And so when we do see differences in graphical structure results, one of the thoughts was, hey, take the structure we see from the causal result and then put that in BayesiaLab and operate it as a p-sum. And then we could do subsequent things that are programmed in BayesiaLab and get causal conclusions that way. But we had other questions, and so we were basically saying, hey, are there possibilities that a machine learned causal structure result could somehow inform causal learning search results? I don't know. I don't know if that's fully answered. There's some people that have some opinions about that, but I tend to be like, look at everything and make use of everything as best as I can and look for the synergy in things. Another question we had is for very large data sets, does it make sense that we use machine learning as a screening function followed up by causal learning? And I know that they have taken tetrad, put it on a supercomputer, and they've processed over 1 million variables and 1 million records. But I can tell you that some of these algorithms do crank for a little bit, and I've not had to wait for BayesiaLab very much. Number 3 here is, could machine learned graphical structure results be an opportunity to inform research into new causal search algorithms? And the reason I bring that up is that there's different machinery behind what tetrad search algorithms are doing, what BayesiaLab is doing with Shannon's information theory. And so I'm just looking to see if there could be a superior result using both of these technologies together. And some of these questions were brainstormed, so they overlap a little bit, but I have to believe that there is some superior benefit that we could define making use of the outputs of both machine and causal learning. If they have agreement on edges in the graph, if they have disagreement on edges, and is there some theoretical basis for looking at the intersection of Shannon's information theory and the causal theory. Number 6 talks to the fact that we do have a few ways from the CMU faculty to be looking at causal search on different parts of what might be a holistic, huge map. And there might be ways to stitch that together, but that's not well defined. I actually believe that maybe machine learning could offer some help in that area as well. So we're seeking research collaboration 2 ways. One is that if you are involved with software projects, have access to software data, we would love to partner with you. We actually have the ability to fund other researchers to work with us over the next several years on this. And then the second opportunity is to just get further insight and answers to the questions we've posed in this presentation. So myself and Mike Conrad are working on this and appreciate any inputs you all might have.